Okay, so we just looked at a couple examples of exponential growth. Remember, that's when your initial value or y-intercept is a positive number and your ratio or common ratio is greater than positive 1, right? Okay, so let's look at this example. Y equals 1/2 to the x power. All right, let's graph a couple values of that. Let's graph -2, -1, 0, 1, and 2, right? And let's see what this looks like. Is it going to look like our exponential growth examples? Well, let's find out. X equals 0 is always the easiest place to start, right? If we look up at y, we just have 1/2 to the x power, right? Knowing that the form of our exponential function is always a times, let's use r to the x power, right? Where a is our initial value or y-intercept and r is our ratio. In this case, it's clear that 1/2 is our ratio. And since we don't see that coefficient a written explicitly, we know it must be equal to positive 1, right? So we should be able to automatically tell you or tell us ourselves that the value of a or our y-intercept in this case is equal to 1, right? But of course, we can also, as an exercise, find that out by plugging in x equals 0, right? We're going to get y equals 1/2 to the 0 power. Of course, what's anything to the 0 power? It's 1, right? So we have the point 0, comma 1. Let's mark that off right here, okay? Here's our point 0, comma 1, our y-intercept, all right? Okay, let's try x equals 1. Let's graph good old x equals 1. We're going to get y equals 1/2 the first power, right? What's anything raised to the first power? It's just itself, right? It doesn't change. So at x equals 1, y is equal to 1/2. 1/2, right, is going to be right around here, isn't it? Right, it's going to be right around there. Okay. Let's take a look at another example. Let's graph x equals 2. What's y when x equals 2? Well, y is going to be 1/2 to the, let me draw that a little bit better. Y is going to be 1/2 to the second power, right? Well, hopefully we remember our property of exponents. That means this is going to be 1 to the second power divided by 2 to the second power. That's going to be 1/4, right? How else could we have figured that out? Well, if we took 1/2 to the second power, right? What does raising something to the second power mean? It means we're multiplying that base by itself, right? 2 times. So we'll have 1/2 times 1/2, right? We know how to multiply functions. That's 1 times 1 equals 1 in the numerator, and 2 times 2 equals 4 in the denominator, right? Either way, we get the same answer. When x equals positive 2, y equals 1/4. So, well, look at this. It looks like our function is decreasing as x increases, doesn't it? And doesn't that make sense if our base is 1/2? Sorry, yeah, if our ratio is 1/2, that means we're multiplying by 1/2, right? In this function, we're multiplying by 1/2 more and more. If we multiply by something by 1/2, it shrinks, doesn't it? When you take a half of something, doesn't it shrink? So it should make sense that as the value of x increases, the value of our function decreases by a half each time, right? Let's graph our two other points. Let's graph x equals -1. We're going to get y equals 1/2 to the -1 power. Okay, this might be a little tricky, but it shouldn't be too tricky, right? When you have a fraction raised to a negative power, you flip the fraction, right? So this actually equals 2 to the first power, which equals +2, okay? So when x equals -1, y equals +2, right up here, right? Right up here. And look, if we plugged in x equals -2, right? If we plugged in x equals -2, what would happen? We'd get 1/2 raised to the -2 power, right? We'd get 2 to the second power, which would equal 4, right? So that'd be even larger. It'd be, way up there over here, right? Way up there. So our graph would look like this, right? Okay, that's not the best fitting line. Let's try a little better than that. Okay, something like this, right? Something like this. Okay, is this exponential growth? It doesn't look like it. As x increases, it looks like we're continually decreasing, right? Well, if you have, again, a positive initial value, a positive y-intercept, but if your b value, if your value of b is less than 1 but still positive, right? Less than 1 but still positive. If your common ratio is like a fraction less than 1, like 1/2 or 2/3 or 0.63, right? You're dealing with exponential. You're dealing with exponential, is that right? Exponential decay. Okay, you're dealing with exponential decay. And doesn't it make sense that if you have a positive ratio, but that is smaller than 1, the value of your function is going to decrease exponentially, right? It's going to decrease very fast and quickly become very, very small, right? And it's pretty much the opposite case of your exponential growth, right? Where as your values of x increase, the value of your function decreases very quickly and becomes very small. But to the left of the y-axis, as your values of x decrease or become more and more negative, the output grows very quickly. So it's really sort of a mirror image of your exponential growth functions. And again, that's when you have an exponential function with a positive initial value or a positive y-intercept, and your ratio is a positive number less than 1. That's exponential decay.